All right, from our first day's work dealing with these optimization kind of problems, we wrote down a list of steps that you would follow in order to be able to solve one of these. Well, step one, remember, is read and understand the problem. As you're writing it down, you're hopefully reading it through and kind of processing through what's happening. Step two of the process is to draw a picture if it's useful. Would a picture be useful here? Well, it actually represents something physical. It represents something in the real world. And anytime it does, I would say that yes, a picture would be useful in that kind of a case. So, here's my box. Now, I want to start labeling the pieces of my box so I know what it's going to be called and all that kind of stuff. So, I'm going to go ahead and call this front edge X down here. And now the tricky question, actually not even necessarily tricky, but the most important question, probably actually the whole thing, to avoid it becoming really complicated. What are we going to label that side? Yep.
X as well.
It is going to be X. Very good. Because you'll notice that in the description for this problem here, it is a square base. Not just a rectangular base, but a square base. So those two dimensions have to be the same, and thankfully so. Because otherwise, we'd end up with 3 variables in this problem just for the dimensions of the box, and it'd be much more complicated. All right, and then for the height of my box, you could use all sorts of different things for it. You could use Y, Z, H, whatever. I'm going to call it Z, just because I feel like it. All right. So now that I know what I'm calling those, I can keep track of it as I go forward and start writing the equations. So the first equation that I normally like to write is the one that involves that big number. In this case, the 32,000. So the 32,000 is my volume. Thankfully, volume is fairly straightforward to calculate here. Volume is always going to be length times width times height in a rectangular prism like this. In this case, that's going to be x times x times x. And so, I'm sorry, yes, x times z. So that would be x squared times z. So length times width times height, just combining the x times x to x squared. All right. Now the next part's the slightly trickier part. The next part's the amount of material that we're using. And the amount of material basically is surface area. So you can choose a name for it here. You could do M for material. You could do SA for surface area, although I've never liked the 2-letter variable names. I think it's just wrong. So I'm just going to actually call it A. It's an arbitrary choice, personal preference. So A equals. Okay, so now I want to start grabbing the areas of each of these sides. So let's start with the base. So I want the area of that base. Well, it's going to be x times x. It's a rectangle, so that's going to be x squared. Plus, now I'm just going to have to add all of the areas of the sides together to know this total amount of material. So next up, the front side.
4zx.
So for that front face, it's x by z, so that would be plus xz. Okay, and then the right side. What's the area of the right face? xz again, right? And so it's plus xz plus the area of the back face. Okay, that's xz. And the left face, yeah, that's xz as well. Okay. What about the top?
There is no, because it's open.
Yeah, there isn't a top here. Because you notice that in this particular case, it must have an open top. So we don't have to account for anything on the top. All right, so seeing the whole picture now, you'll notice there's a much easier way to write that area equation. Rather than x plus z plus x plus z all those times, let's just turn that into 4 times x plus z. All right, we now have our system of equations. And now that we have our system, we do the substitution step. Which means I need to solve this first equation here, either for x or z. Which one do you think is going to be easier? Well, and if you're not sure, think ahead. If I solved it to be x equals, it'd be x equals the square root of a big old fraction. If I solve it for z, it's still going to be a fraction, but there won't be any square root. That seems simpler to me, so I'm going to go ahead and solve it for the z. So we go z equals, and to solve it I divide both sides by the x squared. So that's going to be 3200 over x squared. The other advantage of having just solved for z is that when I go to plug it in here, I'm only going to have to plug it into one place, which hopefully will also make my life a little bit easier going forward. Alright, so let's go ahead and plug that value of z into my area equation. So x squared plus 4x times the 32,000 over x squared. And we're going to have to find the derivative of this. It's going to be much easier to do so, though, if we go ahead and just simplify that first. So go ahead and simplify that. And so you notice we end up with 128,000 over x there, because the 4 times the 32,000, that gives me the 128,000. And then if I put an x on top, but then have the x squared on bottom, I can cancel an x out of both top and bottom, which is why this is just an x on the bottom and not an x squared. That's about as good as we can make it, though, going forward. So now it's time to go ahead and find the derivative. When finding this derivative, okay, the x squared, that's pretty easy, right? But then the 128,000 over x, remember you don't have to use quotient rule there. I mean, you can if you really want to. But you don't have to, because that's the same thing as 128,000 times x to the negative 1. So just use power rule. It gives us a negative 128,000 x to the negative 2. And then I just put the x squared back into the bottom, because my next step is going to be to set this whole thing equal to 0 and solve it. And it's going to be a little bit easier to work with in that form. Now in solving this, I see that I have two terms. I think the easiest way to solve this will probably just be to move one of those terms to the other side. So I'm going to add actually that 128,000 over x squared, and then solve from there. And so when we solve this through, we find that x equals 40, specifically 40 centimeters. All right, now the original question up here asks us to find the dimensions. Okay, so I found part of my dimensions. I found the x. I now need to find the z value. I do that by plugging it back into the first equation, because that's the one that actually had the numbers in it. And to make my life even easier, I can just plug it into this one that I had already solved for z equals. And so I plug the 40 in for x into that equation. And then it's a little bit of calculator work from there just to figure out what z actually equals. And so the 40 squared ends up giving us 1,600. Then we do the 32,000 divided by that, and we should get an answer of z equals 20 centimeters. And so our final answer, what are the dimensions of this box going to be? The dimensions of the box are going to be 40 by 40 by 20 centimeters. All right, so again, first step, you write down the problem, read through it, understand what it's asking about, and then we look to see, is it going to be useful to draw a picture? Well, since this represents a real-world situation, I would think yes, draw a picture. And with this one, it can actually help us avoid some possible errors, because if we just try to keep track of numbers in our head, it actually can lead us to a couple particular mistakes. All right, so here's my picture where I got the big paper on the outside, some blank margin, and then we actually have our printed area in the middle. Now, We got these margins, and the margins are the part that's going to give us trouble if we aren't careful with them. So let's go ahead and start by putting those margins on here. So the top margin is going to be 10, and the bottom margin is also going to be 10. Okay, the sides, each of those has a margin of 6 centimeters. And so it's going to be 6 there, and it's going to be 6 there. By drawing the picture, one of the things we've done is we've also reminded ourselves that it's 10 on each of the top and bottom, and not just one. And so we're going to be notice using that combined margin of 20 instead of just 10. And if we just look at the problem and don't draw it out, we're going to tend to use the 10 instead of 20. All right, the last thing we need to do on our picture is label what I'm going to call these sides that I'm working with. Now we actually have an option at this point. We could actually choose variables to represent the outer dimensions, or we could choose variables to represent the inner dimensions. You could do it either way. However, in this case, the question that it's asking for us is to find the dimensions of the poster, that is the outer dimensions. So I'm going to go ahead and use those as my labels. That way, once I find out what they equal, I'm done. I just have my answer. I don't have to do anything else with them. So since it's a rectangle, I'm going to use L and W, length and width. You don't have to use L and W when you do these. There's nothing magical about them. It just makes sense to me, so I choose to use it. All right, now that I've done that, I put everything into the picture. I can go ahead and start writing my equation. The first equation I like to write is the one that's got the big number in it. That's the 6,000. So it's going to be 6,000 equals, well, remember, it's a 6,000 square centimeter poster. So that's the outer dimensions of this. That's like the paper size has to be that. So this is just going to be LW. Length times width. Because it's the outer dimensions. All right. The other part is we want to maximize the printed area. That is, we want to maximize this shaded region in here. Well, that's another area. So notice both of these equations are dealing with areas, just different areas. But I'm still going to use A for that because it is an area. If you want to choose a different letter, again, you can do that sort of thing. But I think A for area always makes the most sense. It's just that now to find the area of that inner rectangle, I now need to know what are each of these dimensions. So like this dimension right here along the bottom, it's not W, right? It's actually going to be W minus how much? 12. Yep. Because I'm losing 6 from both sides. So I take whatever W normally is, and I'm taking 12 total away from it. And then the same kind of thing happens for my length of my printed area as well. That's going to be the L, but in this case it's going to be the L minus 20 for that height. All right, so now I can write the equation for that printed area. That's going to be the L minus 20 times the W minus 12. Now I have my system of equations. Now we can go ahead and solve for one of those and solve from there. Now, of course, I want to be able to plug into the one that currently has 3 variables and make it just 2 variables. So that means I need to solve the first equation. It doesn't look to me like it's going to matter whether we solve for L or W here. The equations are very similar. L or W is not any more complicated than the other, so we're going to just pick arbitrarily. I'm going to go ahead and choose to solve for L here, but it truly is an arbitrary choice. So in this case, I find that L equals 6,000 over W. Now that I have that, I can go ahead and substitute it back into here. But that looks like troubled waters ahead. That looks like that's going to give me a kind of a messy looking equation when I plug it in there. Now you can do it, but there actually probably seems like another way. My instincts tell me to go ahead and multiply this out. I'm going to go ahead and distribute that because my instincts from having done lots of problems tells me it's probably going to be a little bit easier. So let's see what happens. And yes, oftentimes that's how I decide these things. Am I going to distribute or not? Well, I've done a lot of these and I think it's going to be better this way, so we try it. So if I distribute that in, I get LW minus 12L minus 20W plus 240. Okay, I chose this route, so I'm going to go ahead and live with it. I'm going to go ahead and now substitute that L value back into that equation. So A equals 6,000 over W times W. This is already looking promising, because I know that's going to simplify quite a bit here in a moment. Minus 12 times the L. And the 20W and the 240, those don't change. So having gotten to this point, go ahead and simplify that. Simplify that equation as much as you can. Now when I do the work just to get rid of the parentheses, I end up here. But notice even at this point, I can still simplify it a little bit because I got a couple whole numbers that I can combine. And so I end up with this as my equation. So there's my actual area equation, simplify it as much as possible, trying to make life a little bit easier on myself. Because the next thing I do need to do is take the derivative, and by simplifying as much as possible, the derivative should be easier to find. Remember that 72,000 over W is the same as 72,000 W to the negative 1. And then we're going to set this equal to 0 and solve from there. Now I'm going to need a little bit more room. Okay, so set it equal to 0. And again, I have a binomial there, so I'm going to go ahead and move that 20 to the other side. And then solve from there. And so when we solve that out, you should be finding here that we get W equals 60 centimeters. And then again, this question was asking us for the dimensions. So I want to take that W value and plug it back into my equation to figure out what L actually equals. So let's go ahead and do that. L equals 6,000 over my W value. So 6,000 over 60, L is going to equal 100. So then, those are my final dimensions. The poster size should be 60 by 100 centimeters.